Hello Hambini fans and welcome. In today's episode I'm going to give you a buyer's guide for these bicycle wheels. To give you a bit of context, I actually test these as a service that is provided to a number of wheel companies from across the globe. Wheels give you the biggest performance advantage on your bicycle, even more than the bicycle frame, and the data that you get from testing these, so I subject them to aerodynamic tests, mechanical tests, rotor dynamic tests, is pretty relatable across the board. If you were to take a bicycle frame, you would generally find, because of the size differences, you can get quite a variation between in terms of performance. On a bicycle wheel, that isn't the case because geometrically they are all roughly the same size. Let's start off with some basic geometry. The depth is measured from the outside periphery to the inside. So in this case, on this 9 Velo wheel, it's about 65 millimeters. This is a much shallower rim. It's only about 35 millimeters. The inside width is measured between the side walls, so the sides of the rim. So in this case, it is 23 millimeters. The external is around 28 millimeters. These dimensions are important because it effectively dictates the size of tyre that you can fit onto the rim. Modern high performance rims, road racing rims, tend to be carbon. They're not fully carbon. The insides are a mix of carbon fibre and resin. The other thing that can be added is fiberglass. That changes the mechanical properties of the material slightly to make it a bit more forgiving. Rim construction can be varied. This is what is known as a hooked rim. So if you look very carefully, the edges of the sidewall have a small hook in them, and that is so the tyre can hook into there and is mechanically held in. You can also get hookless, which is a flat side. It's more like a car tyre. There has been quite a lot of contention around whether they are safe or not. In the event of a sideways impact hitting the tyre on a tubeless, hookless setup, you're more likely to have the tyre get pushed inwards and then you get rapid deflation. Rims tend to be manufactured the same way irrespective of the manufacturer. The sidewalls are always thicker because that's where the tyre engages. The bed, where is effectively exposed to air pressure, tends to be a bit thinner. The sidewalls around the cavity, because these rims are hollow, tends to be very thin. Quite often you can actually push these in just by clasping it with your finger. That's not generally a fault. And then the lower section where the spoke attaches is also thickened. Now on some rims, this thickened section at the bottom is all the way around the entire circumference of the rim, so it goes all the way around. On the more expensive rims, it's only local. So if you look at that one, it's quite thin there, but the other side, actually it's a bad example. Yeah, so if you look at this one, this is quite thin there. There's no spoke hole going through. But if you look at this side, this is much thicker. That's where a spoke would go through. So it reduces weight. The really cheap rims are just that thickness all the way around. Some rims that are marketed primarily for tubeless setups, so you have no tube, do not have spoke holes in the rim bed. So in order to get them to be threaded, you tend to have to put something ferrite, something iron or steel onto the end of the spoke nipple and then use a magnet to pull it through. It's a bit of a fiddle. Next on the mechanical list of features are the nipples. So these go on the end of the spokes and they mechanically attach the spoke to the rim. On this particular 9 Velo wheel, these nipples are exposed so you can get at them externally. Some of the wheels that you'll see on the channel have no nipple exposed, so they're actually buried slightly into the rim. It's a bit more aerodynamic. If you buy wheels directly from an OEM, especially the ones from the Far East, these are Windspace Lund spokes, you'll often get a spares pack, not always, but often. And in there, you'll get some spare spokes. Now, in the case of this Windspace wheel set, you can see I've lined up all the spokes on one side, so they're all flat, and we've actually got 3 different sizes. And that is common, so if you're going to replace a spoke, just bear that in mind. This is a carbon spoke. Most commonly, spokes these days are either carbon or steel. Carbon is, I think, probably going to become the most popular type. It's been around for about 5 or 6 years. I think Windspace were the first ones that I got a hold of. They've been fairly trouble-free, and I don't think they are early adopter technology anymore. The spokes, in this case, are mechanically in effectively 3 pieces. So you've got this end, which is the hub end. So that will go into a hub. This is a straight pull spoke. You've got a transition. So this piece is typically metal. This piece is where the carbon starts, and there is a mechanical feature in there to mechanically hold that together. So there's adhesive and a mechanical, it's called a reverse taper. So it's just, as you put tension on it, it gets tighter. Some of the spokes don't have that. Some of the older ones don't have that. And some of the cheap wheels don't have that. If you don't have that, after about 3 or 4 months, especially in inclement weather, you might find the end comes off. This flat section is designed for aerodynamics. So you can see in that profile, it's quite thin. That way, it's quite thick. And then as we get towards the end, we've got another section where we've had to bond mechanically a threaded metal piece, and then the nipple just screws onto the end. So that is mechanically how that goes. So there's 3 parts in there, 2 materials. So you've got the 2 metal ends and then the carbon in between. Steel spokes will tend to be metal all the way down, so just uniform metal that's been drawn, and then one end's threaded. Sometimes they've got J-bends in them. Carbon spokes, like this one, have some very different mechanical properties to their steel counterparts or metal counterparts. They are a lot stiffer, so this is going to have a typical tension of about 140, 150 kilograms force, so around about 1500 newtons. So that's significant. Carbon does not stretch very much, so as you put the tension on, you get to that and it will stretch an absolute gnat's cock. Steel, on the other hand, will stretch quite a lot. The other characteristic that you may wish to have is some damping inside your wheel. So carbon, because of its stiffness, tends to produce quite a harsh ride, but you've got the huge advantage that the carbon is so much lighter than steel. The aerodynamic properties of the spoke are largely related to the T to C ratio, thickness to chord ratio. So a lot of them these days tend to be 0.7 millimeters thick. I can't actually measure that with a tape measure. And then the chord can be anywhere from 3, 4, 5 millimeters. Both of these spokes are made by the company Stren, and you can see the 2 different types that they've got. So this is the 9 velo wheel, and it has a much wider spoke than this one, which is off a Windspace. You can get all sorts of combinations, a plethora of combinations. This is a rare wheel, and any disc wheel will need to have an element of cross lacing somewhere on the setup. This 9 velo wheel is cross laced on both sides. A cross lace is where one spoke goes over or underneath another to give you the cross. Radial lacing is where there's a straight line between there and the rim, and the spoke does not cross anything. Radial lacing tends to give different characteristics to cross lacing. The big reason for the cross lacing is because you cannot transmit drive or deceleration loads via radial lacing. You need the cross. One very prevalent thing that is happening is spoke counts are dropping. So this wheel has a 20 spoke count. I've seen them with 18 and 16 and they're just generally getting lower and lower. The big advantage with a lower spoke count is better aerodynamics because you have less things disturbing the air and it also produces a lighter wheel. But generally speaking, those wheels will have a lower weight limit. Now we're going to move on to one of the most underrated and overlooked parts of the wheel set, the hub. The bulk of hub bodies will be aluminium, usually 6000 or 7000 series aluminium. 6000 series tends to give you a bit better corrosion resistance. 7000 series is a bit stiffer. In the case of this particular wheel set, it has a titanium free hub. So this is a little bit heavier, but it is significantly stronger. And if you have the option, I'd recommend you get it because cassettes won't really touch it. A couple of years ago, a DT Swiss patent ran out, and since then, almost every hub has copied the previous design, which was to use a ratchet type ring instead of a series of pawls. This is a H-Works hub, is no exception. So if you pull the end cap off and take the free hub out, so in there are two bearings. They tend to be 6803 or 15267 with a spring that's designed to transfer some of the load over. You've got the stub axle here and then the two parts of the engagement. So this ring provides drive from the free hub to the wheel hub. So in the top of here, or around the periphery, you should be able to just make out the teeth that go along there, and this spring goes into it. So that's how the drive is transmitted. There's nothing really wrong with the pawl system. You tend to have a slightly bigger diameter for a pawl system to give you the torque load. Personally, I think the ratchet, a ring type system, so the DT Swiss type system, is better purely because when you service it like this or take it apart, you're less likely to lose the bits because they are much bigger. One really big upsell is the number of teeth that are used to drive. So you can get 36, 54, and I think I've seen 72 teeth. That gives you finer engagement. On a road bike, I would say that 36 teeth is plenty. On a mountain bike, you may want to consider a few teeth more. Almost all wheel hubs have the same kind of setup. So you tend to have 4 bearings in the back. So there's 2 actually in the wheel, and there's 2 in the free hub, and then 2 more bearings in the front wheel. These bearings take quite a lot of load. So some of the cheaper hubs tend to use smaller bearings. It makes the hub lighter weight, but they won't last as long, especially if you put some load, vibration or anything like that through it. I've split the ring to show you where the 34, 36 or 54 teeth would go. On some other hubs, specifically I guess the Elite drive hubs, this piece is conical and it should technically give you a higher load rating. So in this design, the mechanism of engagement or disengagement is that recessing, and the corresponding piece in there also recessing. So when it's on drive, the two lock up and hook into each other. On some hubs, these things are partial. So on this one, there's teeth all the way around. On some cheaper hubs, they may only be every 4 or 5 teeth, then a gap, then 4 or 5 teeth, so on. Some of those have been known to fail, so they tend to strip. a common thing that you need to be aware of, especially on some of the sort of AliExpress type hubs, is there's a flange which I'm pointing to with my pencil, and that effectively sets the spacing of the disc. Now you want that to be in a fixed position between wheels in case you have to swap them. H-Works, which this one is, and Shimano tend to be the same. In fact, I've had no issues, you can just swap them in and out. Some other brands tend to have varying spacing, so instead of the disc being there, exaggerated, it might sit here, in which case you'll have a problem. Overall hub designs tend to be fairly similar. However, one contentious issue is around spoke containment. So this hub has full spoke containment. So if you were to lose the tension in, say, this spoke, it wouldn't fall out. Some other designs have an open face. So if you were to lose tension, the spoke could come out. Now in practice, I think that's not very likely to happen, but there have been a few reports, maybe 3 or 4, maybe more. I think it's probably a user choice whether you want that or not, because generally speaking, an open design will be cheaper because it's easier to build. One of the drawbacks to hubs is a lot of the engineering is stuff that most people can't see. So a lot of the cost, the higher cost, tends to come from quality of machining and how good the fits and tolerances are in here. Some slight eccentricity can cause quite a lot of vibration, which people just attribute to running narrow tyres or something like that, but it stems from some eccentric radii inside the hub. Another point is on the cheaper hubs, when you start applying a lot of tension, it actually starts to stretch the hub, so the bearing fits tend to change. Take a closer look at the hubs. This is the front hub, and they are made pretty much all the same way. So you've got end caps on either side. I've loosened these so you can take them off. And then in the center, there's an axle, usually 7000 series aluminium alloy, and then you've got bearings in either side. These are fairly small on the front axle because there's not much load. They're a bit lighter weight. This is a typical rare free hub. Again, you've got the same kind of end caps, so loosen these again. So one off that side, one off the other side, and then the free hub comes apart. Got the ratchet ring in there with the springs, and then an extended axle. In this, we've got 2 bearings, so typically 6803s in there, and then quite often these ones are 15267. So in a H-Works hub, which this is, they're quite big. I've already talked about the fits and tolerances being different. The other key difference is the ability to service. On this particular hub, you don't need any special tooling. You can actually just use a mallet to knock the bearings out. But on some of them, and the absolute DT clones, you need a special toothed engagement tool to get in there and then remove that bearing. The bearings in the back of any wheel set, because of the weight that's on them, and it's quite a harsh condition because of the vibration from the road, they tend to wear out through actual wear. The front bearings, they tend to wear out mainly through contamination. You generally won't wear them out through wear. An area where quite a lot of cost cutting takes place because you can't see them is in the bearings. Bearing quality varies considerably. A lot of these hubs use bike specific bearings. This one doesn't. This one uses standard 6000 series bearings. You can pick them up in pretty much any bearing shop, bearing counter. Bike specific bearings, even in a bike shop, you may struggle. So if you actually have a set of DT Swiss hubs, you'll find some of those bearings are specific to DT, even though they are labeled differently. In terms of manufacturers, 3 of the biggest. So we've got NTN, FAG, Scheffler, NSK Toyama, Between them, they probably have, at one stage, they probably had about 40 or 50% of the entire market globally. These days, it's nowhere near that. These bearings are of very high quality. So the races are hardened. So if you were to get like a Stanley blade, a utility knife, and try and scratch that, you wouldn't be able to. And the dimensions are very good. So they're dimensionally very accurate. The only perils of this is buying a fake, right? So at the moment in the UK, there are a lot of fake NTN bearings. Not so much FAG, not so much SKF, not so much NSK, but certainly NTN, a lot of them are faked. One of those big things that happened probably 5 or 10 years ago was there was a general desire to get ceramic bearings for your bike in the on the premise that they would give you less friction. The reality is most of the friction actually comes from the seal. So if you have a full contacting seal, that will give you way more friction than the ceramic balls in there. Ceramic balls also are a poor choice for a wheel because vibration causes the very hard balls to pit the races. They can be hardened, but ceramic is way harder and it will, pit. That's why you generally won't get cars with ceramic wheel bearings because it's a known issue. Another popular one is stainless steel. These ones are chromium steel, bearing chrome steel. Stainless steel is very, very soft. So while it might present excellent properties in terms of corrosion resistance, in terms of actual rolling resistance, and also in terms of cost, it's not so great because after a little while, it'll pit and tend to gall. So while it won't fail through corrosion, it will tend to have worse vibration characteristics. Now, people are quite often under the illusion that all you need to do is service the bearings. In reality, what's happening is the pits and the galling's already there. All you're doing is putting new grease in there to mask what you already had. Right, aerodynamic considerations. The first thing is rim depth. Rim depth is the biggest contributor to aerodynamic performance. These two charts, one is at 50 k's, this one's not labelled but it's at 30 k's. You've got rim depth along the bottom here and then power along the side. There's a definite correlation that way. Just be aware that even if you pick, let's say, the 50, these dots do not correspond to the same positions at a different speed. So you may have one wheel that is actually slower at 30 k's and becomes the fastest at 50. Deep wheels are faster for two predominant reasons. The first is the tip velocity. So where I've drawn these two circles, we've got the shallow wheel on the left and the deeper wheel on the right. This point here, which is the tip of the spoke, so where the nipple is, that has a higher velocity on shallower wheels because the radius of the spoke is longer, and that creates more drag. The other is less spoked area. So on the deeper wheel, this area here is smaller than this area here. The deeper wheel has better constrainment. So if you have a solid surface, air it can't penetrate it, so it has to generally follow it. That will give you better aerodynamic performance. The ultimate example of this will be a full disc. Now, in terms of actual, geometry, there are a few things to look at. The chord to thickness ratio. So this is a section through a tyre and wheel. So you've got the tyre here, the tube here, spoke here, and this is the rim around here. You want that ratio to be 4:1 or greater. It's not so easy these days because wheels have become considerably wider than they used to be. There are some other features you want to look at, and this one is a big one, the transition. So where the tyre meets the rim, so this is a hooked rim, that point there can generate quite a lot of drag. And alpha critical, again, this one's a bit more of a tricky one, but it's the angle at which the air would leave in a straight line through the section. Because if you were to take a wheel, let's say like that, you would find if you took the cut here as opposed to through the middle, you would actually end up with a profile that looked like that. The rim shapes, this was all the rage not that long ago. So we had these toroidal shapes like this one, I've highlighted number 2 and number 8, and the more pointy ones, which are like number 4. These days, because the rim is so wide to accommodate the wide tyres, it's not so important. The wavy profiles and the skin friction aero. Skin friction is the drag generated by air actually rubbing against the surface. These dimpled surfaces that are here, they're there a bit like a golf ball to generate a turbulent boundary layer. It's designed to keep the air attached for longer before it detaches. I've had, well, fairly mixed results in testing them. They will generally only work at a certain velocity. If you go either side of that, it generally won't work. These sawtooth designed wheels, so the Zip 454 is an example, they will generally be heavier than a wheel of equivalent depth. You're also making a bit of a compromise there because the effective depth is there, but you're losing the aerodynamic benefit, and then you're only getting that there. Again, this is one of those things where if you are at the exact speed that these were tested at, fine, it will give you a marginal benefit, but for the rest of the time, if you're accelerating to that speed or have gone past it, it's not really worth it. In sequence, this is what I would pick if you were going to get something. So first of all, consider the rim depth plus the rim width, if that choice is available. It usually isn't. The wheel to tyre transition, spoke nipples, spoke to cord thickness, and the number of spokes. These three are less important than these two. These two have very good, I got very good high confidence ratio in those. Right, mechanical consideration. So runouts and fits. This is like a schematic of a typical hub. You've got the disc brake on this side and the free hub on this side. So this is the rear. And this is what it would look like through the middle. So you've got 4 bearings there. That one there, that one there, there, and there. All of these things should be concentric. So if we go to this slide, what I've done is I've drawn the perfect one here and then one here which has a bit of eccentricity. So you can see these 2 red lines here and here. They are the center lines of the bearings. So the free hub has some eccentricity to it. Now, it's only small, so where I've pictured that, it's just there for exaggeration, but that is really what I mean by concentricity and eccentricity. Additionally, each of these bearings are designed to go into a bearing seat. If those seats are too tight, you'll find the hub starts to bind slightly. Now, ride quality is something that people talk about. One of the main things is, and people don't really consider this that much, is when you are at speed, the wheel will actually start to bend. So here we've got the wheel at rest, and here we've got the wheel at speed. Now this is exaggerated. Your hub isn't going to move by that much, but the wheels is flexible. So any sort of out of balance, imbalance, or even deflection from the road will send the wheel away from its normal equilibrium position. Now at speed, that deformation away from its equilibrium position carries on, and that will make the vibration even worse, and you'll feel that as harshness. Now you can minimize that by minimal runouts and better balancing. So in practice, what we've got here is speed in RPM. So that's wheel speed along the bottom and then vibration along the side. I'm just going to erase the ink. This is a well-engineered wheel. this one is a moderately engineered wheel with steel spokes. Now, if you look at this, the vibration where it exceeds 2 is at like 550 RPM, whereas on this one, it's about 225, so it's half that. So what that's saying is this wheel is starting to bend at basically double the speed. So this wheel on the left-hand side will give you way more consistent handling. If you were to ride this wheel on the right-hand side, sort of in this range, you are liable to get more wheel wobble because the wheel has basically deformed. It doesn't deform very much, but it's enough. So there's the wheel starting to bend and the other's wheel starting to bend. So the mechanical bits at a glance, I recommend you get decent hubs because the realistic bit is you're not going to be able to measure them. So get something reputable. I think the one to get at the moment is H-Works. That's widely regarded as the best. Now, high spoke tension variation often means there's poor run out because you might have a slight error in the hub, and in order to correct it, people are adjusting the spokes to bring it back towards the middle. Most people don't check the run out at the hub. I recommend you balance the wheels. That's something that people don't do, and especially important if you've got tubeless wheels because the sealant can congeal and send the wheels out of balance. Rotate the tyre so the heavy spot acts in your favour. So if you do basically a static test, you can find some videos out there on the internet. You can rotate the wheels so that the heavy spot counteracts the wheel rim heavy spot. And lighter wheels are more sensitive out of balance. That might sound counterintuitive, but as we head towards sub 1 kilo wheels, that balancing becomes more important. Now, a lot of harshness is actually self-inflicted, so people are basically trying to improve their ride by fitting wider tyres because it's more damping, but a lot of that harshness is from having poor runouts and moreover having unbalanced wheels that actually deflect. Right, if you've got any questions or comments below, remember to whack them down, and if you've got any other issues, send us an email. Remember to like and subscribe. Till next time, keep banging your hairdresser.